I guess it was fine. Okay. So we're going to be talking about titrations. All right. And so you'll be actually doing one of these in your lab class as well. So just to kind of give you an expectation of what's going to be happening, this is going to be an acid-base reaction. Right. So we're going to have this sort of instrument here, something called a burette. And it's going to be filled with base, right? That's how you're going to start off. And then you're going to start off with a flask that's filled with acid. Okay. So this is before any sort of reaction has happened, right? You have acid in one flask, you have your base in your burette. The thing in the burette we call a titrant. And again, for your particular experiment, it will be the base in the burette. You could design an experiment where they were flipped, where it was acid in the burette and base in the flask. But for this particular one, you're going to have base in your burette. And at the start of your experiment, there's going to be no reaction that's occurred. And then you're going to open this little mechanism here on your burette and start slowly adding base to your flask. Okay. And when you add base, it will react with the acid molecules in the neutralization reaction. Right. And so you'll keep on going until you hit what's called the end point. Okay. You're going to have an indicator in that flask, which changes color as soon as all of that acid is consumed. Right. That will be the end point of your titration. Okay, so basically you're sitting there, you're adding base slowly, slowly, slowly until you see this color change occur, and then you stop. And that's what, with that endpoint, is what we call the equivalence point, where the concentration of acid is equal to the concentration of base that you added. Okay, so that's sort of how this is going to go down in the lab classroom. For us, in terms of our pencil and paper chemistry, we have a pretty defined goal with these titrations. And that is to be able to calculate the pH at any point during that titration. So both at the beginning, before we've added any base, in the middle, as we're still sort of adding base, but there's a bunch of acid, at that equivalence point, and afterwards. We want to be able to calculate the pH at any point along that titration scheme. That's our goal for today. Okay. And again, we're going to see that it's broken into 4 main regions here, this titration curve. And that's going to be important to think about as like sort of dividing lines in your mind, because we're going to have a different approach for each of these 4 locations, or each of these 4 calculations. All right. So in general, we're going to have this general strategy. Okay, because this is a titration, because you're constantly adding volume to your flask, right? When you add base to your flask of acid, you're changing the volume of the system, which means that concentrations are going to fluctuate quite a bit. So in terms of general strategy, we're going to be converting to moles to calculate how much acid/base we have. Right? We're going to have to do our ice tables in moles because the volume is changing. This is very similar to what we discussed last class when we were doing those hard buffer problems that talked about mixing 100 milliliters of this weak acid with 200 milliliters of this conjugate base. That was this last problem we did last class. And what we had to do in order to figure it out was to first convert to moles, because those volumes were changing. We're going to have to employ the same strategy here, because in a titration, our volumes are going to be changing. Right? So we can always get concentration after the fact by taking account for how much volume we have. But in terms of measuring how much reaction occurs, we're going to have this same general strategy, convert to moles. All right. And then our titration, again, we got these sort of like 4 regions of our titration that we got to pay attention to. The first one is before any titrant is added, meaning before you've even started your experiment. You poured your acid into your flask. What's the pH of the acid in the flask, right? Before any reactions occurred. Our second region here is going to be after the titrant is added. Whoops, that's not how you spell that. But before the equivalence point. And again, that equivalence point, the definition of that equivalence point is when the concentration of acid is equal to that concentration of the base that you've added, right? You've added just enough base to react with all the acid in the flask. That's the equivalence point. So the third segment is going to be at that equivalence point. And then the fourth region is after. All right. So again, we're going to have this general strategy for our titration calculations. Our goal is to be able to calculate the pH at any point during the titration. We're going to have to convert these to moles in order to figure out how much base and acid are reacting with one another because our volume is changing. And then we're going to break it up into these four regions: before any titrants added, after the titrants added, but before the equivalence point, at the equivalence point, and then after the equivalence point. We're going to see we have a different strategy for each one of these regions. All right, so first type of titration we're going to look at is strong acid, strong base, right? So we're going to take, for example, HCl as our acid and NaOH as our base, both of which are strong acids and bases. And remember, strong means that they are fully reacting, right? That reaction of that acid and base are always going to go to completion. Okay, so let's look at one of these curves here. So this would be, as I said, our goal is to be able to calculate the pH at every point in this titration. So if we did, I don't remember how many this is, like 1,000 calculations, each for a different point in the titration, we would end up getting a curve that looks like this. All right. And so basically our goal is to be able to pick sort of a region here and to be able to calculate that that is indeed the pH in that region. All right. So again, let's break this up into our four regions that we were talking about here. Over here at the very beginning, right? This is before the pH of this solution. And I guess actually, let me be clear. On this on the y-axis here, this is the pH. And on the x-axis, move it up so I got a little room. This is the amount of base added. All right, and you don't know how I got these numbers yet. We're going to get that. That's what we're going to build up to here. All right, so for right now, you're just going to trust me that this is indeed what this sort of curve would look like, this titration curve, and we're going to work to sort of pick it apart here. All right, and then we'll sort of take the step of being able to calculate the pH at each of these points. All right, so again, at the very beginning here, this point with 0 base added, that's that first region we were talking about. Right. And again, I'll actually copy them over here so we can take a look at them. This is before any titrant has been added. All right, region 1. We'll go ahead and color code these. Okay. My equivalence point is this one right here in the middle of that sharp curve, right? We basically have our pH slowly increasing, and then all of a sudden it sharply curves up before flattening out again. The midpoint of that sharp curve is our equivalence point. Right, that would be this third region that we had talked about. So that's going to be 3. So then between 1 and 3, that's the second region where we have added some titrant. So this whole thing here, after we've added some titrant, but we haven't quite reached our equivalence point yet, right? So that's region 2. And then region 4 would be anything after that equivalence point. Right, so then this region here is 4. Okay, so these are our 4 different sort of regions of this titration curve. And again, our goal is to be able to calculate pH at any point here. And we're going to see that we have a different strategy depending on what region that we're in. All right, so let's take these sort of one at a time here. The first one, before any titrant added, this is going to be the exact same as calculating the pH from chapter 17, right? Given a solution of acid, whether it's strong acid or a weak acid, we learn that we can calculate the pH of that solution. So that's exactly what that first calculation is going to be. We don't even have to know that there's a titration going on, right? For that particular one. So let me sort of put some real numbers in here in terms of how we're going to go about solving this. So a problem would look like this. I'm going to have to get rid of these markings. So all right, yeah, let's just start. So what is the pH? All right, if you prepare a liter of 1 molar hydrochloric acid, what is the pH? I want everybody to take a minute and tell me what the pH of this solution would be. Again, this is something that we should definitely know based on what we learned last week. And I just want to sort of emphasize that I have some sympathy for not everybody being on the same page up until the point that I took over the course. But since taking over the course, I've made sure that my expectations as to what we know how to do are clear. And this is definitely one of them. So if this is something that you're like, I have no idea what's going on, then you really need to go back and do some review, because at this point, this is something that we got to know. All right, and I'm going to open up a short answer poll on our iClicker. I have no idea how this is going to work because I've never used this one before, but in theory, you should be able to enter the number that you get for your pH. So I'm going to give everybody a minute or two to calculate this pH, and you're going to enter it in on this iClicker. Well, let's see how this short answer function works. Again, I'm kind of still learning iClicker here. All right, so what made these problems for the strong acids relatively easy compared to our weak acids was the fact that because it's a strong acid, we can say that the initial concentration of HCl that I have, that's just going to be equal to that hydronium ion concentration at equilibrium, because we're going to have this full dissociation of that acid, right? So in order to get the pH, I just take the negative log of that hydronium ion concentration. All right, so I'm going to give you all another 20 seconds to get your final answers in here. All right, and so I take the negative log of 1, that concentration of my hydronium ion, and that gives me a pH of 0 to start out with. If I'm being good about sig figs, it's really 0.00 because I have 2 sig figs in this concentration. So I should have 2 decimal places in my pH. All right, so that's my pH at my starting value here, right? And again, for that first region, we'll sort of take notes, little cheat sheet notes here. Let's see if I can't make more room. For that first region, there's no reaction. So we calculate pH, just like chapter 17. All right, so now we're going to move on to this second region here, equivalence. All right, this is after some titrant has been added, but we're still before our equivalence point. So our goal, let's go back to our graph. Let's pick this point right here where I've added half a liter of my base. All right, so now we're going to update this problem. So student prepares 1 liter of 1 molar hydrochloric acid. .50 liters of 1.0 molar NaOH has been titrated in. What is the pH? All right, so here is our goal, is to figure out now in region 2, when I've added a little bit of base, how does that change my pH? Okay, and one of the things that we're going to have to remember again is that strong implies fully reacts. Okay, so we're going to write down our, and this is going to be where it gets a little tricky, because the first thing I'm going to do is account for the reaction. Right, my reaction between my acid and base. I have to account for how much base has reacted with the acid. And then in a second step, I'm going to go back and calculate the pH. All right. So first thing I got to do is I got to look at my equation for the reaction between acid and base. So HCl plus NaOH. This is going to go 100% to completion here to give me H2O and NaCl. All right. So if I start out with an initial, and again, we're going to have to convert to moles here. Right. So I can't do this just in terms of concentration. So when I build my ice table, I'm going to have to do moles. I'm going to have to go somewhere else to make more room here. Let me go to another page. All right. So convert to moles. I want everybody to fill out this ice table. This first line here where we have moles of HCl, moles of NaOH. And it actually doesn't even matter what the water, I mean, we could figure out moles of water and moles of NaCl, but I'll show you why that isn't a big deal here in a second. But I want everybody to take a second. If you can't get from a concentration and a volume to moles, that's not a great look. That's definitely something that we need to be able to do, right? Remember, these molarity is moles per liter. So if I take my volume and I multiply it by my concentration, liters will cancel out and will leave me with moles. All right, so moles, if I'm starting out, my volume times my concentration for HCl, that would just be 1.0 moles. And for my starting concentration of NaOH, I have my 0.50 moles, right? I picked kind of easy numbers, so that's why they work out that way. But again, this was just my 1.0 molar times my 0.50 liters. And again, liters will cancel out, leaving me with moles. Okay, so now how do I get the change here? Usually, or previously, we had left this change as a variable. But here, I know exactly how much is going to react because I have a strong base here, meaning that 100% of that strong base is going to react, right? Because that's what it means to be strong. So this is because it's a strong base, right? And because this is a 1-to-1 mole ratio, if I have half a mole of base reacting, I also have half a mole of acid reacting, right? Because every one of those base molecules is reacting with one acid molecule. So my base, since I had less of that, it's going to all be consumed. And my hydrochloric acid at the end here is going to have a 0.50 moles of HCl. All right, so step one, we had to account for the reaction. We did that in moles. Step two, calculate concentration of our acid. Okay, remember that concentration is moles per liter. So I need moles of HCl divided by liters of this solution. My moles of HCl, I'm just going to take what I calculated in my ice table here, that 0.50 moles of HCl. But now what is the volume of the solution going to be? Everybody, I'm only gonna give you a minute here. Let's take a minute and see if we can't figure out based on this problem what the volume of my solution is gonna be at this point. All right. Yep. So my volume, I've now combined my 1 liter with my 0.5 liters here, right? I started out with 1 liter in my flask, and then I added half a liter of base to it. So then my volume has increased to 1.5 liters of solution. So my new concentration for my HCl is going to be this 0. And then we got a bunch of different, yeah, because it's a third. So keep those going. Molar HCl. So then calculate the pH at this point as well. And again, the nice thing is that we can just assume that the concentration of hydrochloric acid is equal to that concentration of hydronium ions. All right, so then I'm just going to take the negative log. I'll keep my sig fig marked. All right. Look, I'm going to go easy on you on sig figs, especially since they're a pain in the butt for pH. You're going to hear me talk about them because I think it's important that we remember that they exist. But these will be multiple choice problems, so I'll kind of be kind about it when it comes to sort of picking answers here on an exam. But nonetheless, it is good to sort of refresh our memories that they exist here. So I'm going to take the pH, which is the negative log of that hydronium ion concentration. And that gives me to a pH of 0.4771213, or rounded to the correct number of sig figs, I should have 2 decimal places. All right, so first we had to account for the amount of reaction that had taken place, and then we were able to calculate the amount of hydrochloric acid, the concentration of hydrochloric acid that remained after that base was added and reacted with it, right? The base took some of that hydrochloric out of the system, but it left some behind, which is what contributes to the pH. All right. Now, our equivalence point here. So now let's say that I've added, we're going to move on to this third calculation, and now it isn't 0.5 moles, but now 1.0 liters of 1 molar NaOH has been titrated in. What is the pH, right? So this is the equivalence point where, if I do my formula again, here I have added the same amount of acid as I have base, right? And since this reaction goes 100% to completion, that means that I'm left with only my 2 products, water and sodium chloride. Right, so we can use the chat for this one. What do we think that the pH is going to be at the equivalence point for this strong acid, strong base reaction, when this reaction that I've just drawn on the screen here has gone 100% to completion and there are no more acid and base left over on the reactant side? Awesome. So at that point where acid and base are exactly equal, all I got is a solution of salt water. And sodium chloride definitely isn't going to do anything to change the pH of that solution. So indeed, for a strong acid and strong base, the equivalence point is always at 7. All right. And then after that equivalence point, now we're going to go back. So now let's say that we're going to do one last calculation here where we've added 1.5 liters. All right, so now we have more base than we had acid. Okay, again, we're going to have to do the same thing we did for region 2, which is to account for the reaction in moles. So I'm going to start off, I'm going to clear my ice table here. Although I'm going to start off with those same number of moles of hydrochloric acid, right? I didn't change the amount of starting material that I had. But now I'm going to figure out how much base I had. And since I started out with 1.50 liters of 1 molar NaOH, I'm going to do my volume times concentration again, and that will take me to 1.5 moles of NaOH. Let's just be good and write our moles here. Now, if I'm going to look at the change that occurs, again, strong reacts completely. But this time I have more base than I have acid, right? So my limiting reactant here is going to be the acid. That's the one that's going to get all used up. I can't possibly use up 1.5 moles of acid because I just don't have that much, right? So I'm only going to use up my 1 mole of acid, and that's going to completely react with 1 mole of base, leaving me with 0 moles of acid and 1.5 moles of NaOH. Right, so now when I go to calculate my pH, I'm really going to first have to calculate my hydroxide ion concentration, or rather, I guess my concentration of NaOH. And then the nice thing about it being a strong base is I'm going to get to say that my NaOH concentration is equal to my hydroxide ion concentration. And again, this is because it's strong. All right, so everybody take a second. Given that we have the concentration of NaOH equals moles of NaOH over liters solution, everybody take a second and see if you can't fill in this concentration here. What is it going to be for the concentration of NaOH? Right, and the tricky bit is make sure that you're accounting for that volume. So like we had said, we got this 0.5 moles of NaOH left over after the reaction. And now our volume is going to be the 1 liter we started with plus the 1.5 liters that we added. So now we're up to a volume of 2.5 liters of solution. Okay, so this is 0.2. Do I only have the one? Yeah. Molar NaOH. Oops, this needs to go away. So I can take the negative log to get my POH, and then I can take the fact that 14 minus that POH is equal to my pH, right? So the negative log of OH minus, this will give me my POH, and then 14 minus the POH gives me the pH of the system. And so what I would find is that I would get a pH of 13.3. All right. So this is the strong acid and strong base titration curve here. Importantly, because it's a strong acid, strong base, the equivalence point is going to be at pH 7, at a neutral pH.